Okay. Alright, so we're going to construct confidence intervals. Now what I want you to get out of this lesson is knowing how and when to use sample means and sample standard deviations. Alright, and we're going to use them as estimates, the best estimates for the population parameters. So if you don't know what the population parameters are, if we don't know what the population mean is or what the population standard deviation, okay, because we just haven't looked at the whole, unable to measure or examine the whole population and all their data. We just look at a sample and we use the statistics from the sample and we use them as like a best estimate. Does that make sense? And we're going to form 95% confidence intervals, okay? And we're going to see that the interval is found in this description. It's a multiple of 1.96 multiples of standard deviations on either side of the sample mean, okay, or sample proportion. Now that means forming an interval. And an interval, think about how you did that in maths methods. An interval was like when we're finding domain and range of a function. We formed an interval, didn't we? And you remember the interval notation? Yeah? Some number x is in between a minimum to a maximum value. Alright, we're going to do the same thing. Okay? So let's start off with just reviewing what we did last lesson, looking at some mean and standard deviation, okay, of a sample mean distribution or sample proportion distribution. Now, from last lesson, the last thing we did, we looked at the distribution of sample means. Hi Karen, how you doing? It's good that you showed up. Everyone was doubting your attendance this morning. Alright. So from the distribution of sample means, there's a typical shape of the distribution of what you got in our Google Sheets simulator. Okay? That was the distribution of heights. Yeah? And you can see it's got this kind of bell-shaped curve. Alright? So the center of the distribution is the mean. It's the expected value or the expected value of the distribution of all the sample means. Okay, and we can see that's the same as the population mean.
I didn't leave my keys, sorry.
No. And then the spread, the measure of width of our distribution is about from the center, about the center of the distribution. You've got one, red line from the middle out to the side. That measure there is the measure of the standard deviation of the distribution. Okay? And it's given by this expression. So this is the population standard deviation divided by the square root of n. N is your sample size. So as the sample that we are looking at is large or increases in size, what do we say about the standard deviation of the distribution? How's it? It gets smaller and smaller, that's right. It's going to get thinner, so this is going to shrink. Yeah. So let's try an example. So we've got a total of 1,000 students studying a statistics course at this Mini Trees University. Cool, who wants to go there? Alright, so on a recent exam, the mean score was 90.5. Okay? And a standard deviation of 10. So at university exams, it's not, you get you get the whole course enrollment, sit the one exam at the one time. And usually university courses like 200, 300, 500 kids. Well, I shouldn't say kids, young adults. They're kids from my point of view, I'm 34. So you can't measure all of them. So perhaps if we take a sample of 15 students and select it, then the mean score is found from the sample. Let's find the mean and standard deviation of the distribution of all the mean scores in the sample. So the mean of or expected value of the mean scores is this guy. And it's just to be able to recognize that it's the same as the population proportion. Okay? So from the question, what's referring to the population mean? That's correct. Yep, there it is. It's the mean score of the exam was 90.5. So there's no math there, it's just recognizing that you're looking for the mean of the population. Alright, now the standard deviation, this is the next thing, the standard deviation of the distribution of our sample means is given by the population deviation divides square root n. Okay, so what values do we use from the information in this rule? What's going to be this value in the numerator, the population standard deviation? What is it?
No, sorry.
The 10, that's correct. That's when it refers to the standard deviation of the whole exam. Yeah, that's what this standard deviation is referring to. So that's a 10 divided by, now the n is the sample size. So what sample size are we referring to? Yep. Yes, now got to refer to the size of the sample taken. So that's the population. Okay, well that's the sample size. So it's the square root of 15. Okay. There we have it. So let's just, I'm just going to express this as a third in a simple form. So we have 2 root 15 on 3. Once we rationalize that root 15 at the bottom, we get something like that. And you can calculate that to 1 or 2 decimal places. Okay. Multiply the top and the bottom by root 15. Okay. And just evaluate that to maybe 1 decimal place. Now, let's discuss what's going to be the effect. The effect when increasing the sample size, okay, to 30. So it goes from 15 to 30. What's that going to have an effect on the mean of the distribution? No effect. Good. Okay, because the mean is just the same as the population mean, and that's not dependent on the sample size. And then we can see the standard deviation is dependent on the sample size, isn't it? Okay. So as the sample size increases, the standard deviation of distribution gets smaller, it decreases. Okay. So the width of our distribution here will become thinner and taller. Okay. Any questions regarding that? All right. So you've got 2 sets of formula or things of measures of the distribution. You got to remember you've got your population proportion or your sample proportion distribution. Okay, and you've got those 2 rules. That's what from our previous lesson, that were these ones. Okay, that's for the proportions, P or P hat. So there's the mean of the distribution of P hat, there's the population proportion, and the standard deviation of the distribution of P hat. Okay, you got those 2. And then now we've got means. Okay, sample means, calculated values. Okay. Alright, so questions similar to this is what was on the coursework. Okay, in exercise 6.6, who's made a start of that? Not yet? This is we're doing this weekend, over the weekend, please. So, we've got some information about the population. We've got a population of 200 and the proportion is 0.5. Okay, some population proportion is 0.5. Could be, 0.5 of males in the population, perhaps. Okay, or it could be, 0.5 of people who are dibbing left, right, and centre in the classroom. You haven't seen that? My son at primary school's going off about, oh, everyone's dibbing. Do you know what dibbing is, Dad? No, I don't know what dibbing is. Okay. So, what is the likelihood of selecting a sample of 10 where the sample proportion is between 0.4 to 0.6? So that's like a probability problem. Now, who remembers how to find probabilities of different possible sample proportions? Okay, this is how we did where we set up a probability table. Yeah? So we've got the sample proportions from 0.4 to 0.6. So let's set up a little table, and we're going to work out the population of achieving those proportions. 0.4, 0.5 to 0.6. Okay. When it's written like that, we call that an interval. Okay, it's an interval of sample proportions from 0.4 up to 0.6. Okay? Now, you have to think about if I've got two things and the proportion of one of those things in the population is 0.5, then what's the amount? What's the split in the quantity of those two things? We've got a population of 200 altogether. So how does the quantity separate? Half each. So 100 of one thing and 100 of another thing. Okay? It might be, gender. 100 males, 100 females. Okay? Might be...
Animals versus humans.
Yeah, exactly right. What was that one?
Animals versus humans.
Animals versus humans. Okay. So... And we're setting up the expression involving combinations. Okay? Now, if we have 0.5, then we've got 100 of each as the amount of things we get to select from. Okay? Now, for the sample proportion of 0.4, okay, then what will be the split now of the 200? So we have to see that 0.4 of 200 gives us how much? Okay? So you've got 80 of one thing, and how much of the other? 120. Okay? So that will be the split for sample proportion of 0.4. Yeah? Alright. Now, let's look at the size of the sample. Of 10. Alright, let's do that now for the sample size of 10. So if we've got a sample proportion of 0.4, how would the sample distribute itself? So there's 10 in the sample. Okay, so 0.4 of 10 is
4.
4. Yep. And 6. So the bottom numbers here, yeah, they have to come from they have to be the amounts coming from the sample. So for a 0.4, we've got 4 of them. Yeah. And 6 from the other. All right. So what's the combination of 4 out of 100 and 6 out of the 100? Now, what's the denominator going to be? 200. Yep. And 10. That's correct. So it's the total number of samples we can get of sample size 10. Okay. 10 things from a population of 200. All right. Good. Now, what will be the next one?
5 and 5 in the bottom. So that'll be 100
Yep.
and then 5.
5. Good.
And then the same for the other one.
Yes.
And the bottom one.
Yep. Denominator stays the same. There we go. All right. And then the last one. Yes, very good. Opposite of the first one. So from 100, now we've got 6, 4, 210. Okay, so that gives you all the calculations you got to do of the expressions of combinations in order to work out the probabilities of each proportion. Yeah. Okay, and then that gives you an associated probability that we can calculate. And so if you think about what's the likelihood of selecting sample size of 10 within this interval, then we want to know the probability where p hat is 0.4, or the probability where p hat is 0.5, or the probability where p hat is 0.6. How do we work that out? What do we do, Barissa? Yes, we evaluate each on the CAS, but how do we get the probability of this whole interval?
You add them?
You add them, very good. So it's the probability of the first one plus the next one plus the next one. Sorry? Yes. Yeah, they will. You can see they're the same expressions, just the order in which the multiplication happens is different. So what values did we get? We managed to find the first one.
0.208.
0.208. Yeah. So that should be the same as the last one.
And the middle one is
0.25. 0.25. Very good. Okay. All right. So then we add them to get the probability of the whole interval. So the probability that the sample proportion is in between this interval, that's what we're after. Okay. That's me. All right, and we get our result. So, point 0.66 something.
Yeah, 0.66.
Yeah, 0.66. That's right. Approximately. Hey! These sneezing will be forever and captured in a video on YouTube. All right. Alright, so 10, let's calculate the mean and standard deviation of the distribution of sample proportions of size 10. So what is the mean of the sample proportions going to be? What is the mean of the distribution of sample proportions? What's that the same as? The mean of the distribution of sample proportions. So you've got to think of the graph of sample proportions. What works out the center value of the distribution of sample proportions? What's that the same as? It is. We're looking for this idea. There's the distribution of the sample proportion. So the mean or the expected value of the distribution of sample proportions is the population proportion, P. Okay? It's the actual proportion, the true proportion about the population that we're looking at. Not just the sample, but the actual population itself, which is 0.5. Okay, and then the standard deviation of the sample proportions must be, now what's the rule? Who remembers? Square root of P1 minus P on N. Very good. Okay. Okay, so P is 0.5, so it's 0.5 times 0.5. 0.25 divided by a sample size of 10. Okay? Which is 0.025. Okay. Which is 0.05. You can do that. 0. How many zeros? 2 zeros.
What do you guys get? I have no idea.
Square root.
It's 0.116. True. Yeah, same here. Yeah, 0.16.
From here.
Oh wait, you have to divide it by 10 too.
Yeah.
Divide it by 10.
That's already divided.
It's 0.16.
Okay. Good. Yep.
Yeah, so you can't actually get that with fives. It wouldn't work because there's only one decimal place. If there's two, then
Yep.
yeah, that makes sense. Has to be 0.16.
Okay, there we go. Now, we can describe for yourself if the sample size was increased to 20. Okay, so we're going from size 10 up to size 20. Then, how is that going to affect?
Did you say nothing?
Sorry?
Did you say nothing affects it?
Nothing affects which measure? The mean. Yes, nothing's going to affect the mean, so the mean is not going to change. It will always stay 0.5. But as the sample size increases, then the standard deviation decreases, gets smaller. So this number will be even smaller. Okay? Very good. All right. So that's the exercises that for exercise 6.6, similar to that I'd like you to practice, and they are some of the questions on the exam. Okay. All right. Everyone get the hang of them?
Wait, so did you say 12 or?
Almost. We're getting there. So let's have a look now at the next idea. Now, this here is a typical exam type question, which draws on the formula we just looked at. Okay, but you've got to use them in slightly different ways. So we'll say we've got a student performs an experiment in which a computer is used to simulate drawing a random sample of size n from a large population. Just like this, like what we've done with our Google spreadsheets simulations. Okay? Now the proportion of the population with the characteristics of interest to the student is P. Alright, that's what we're looking at. We're drawing left-handed people, so what's the proportion of left-handers? P. Okay? Now if P is a third, that's the population proportion. Find the smallest integer number of the sample size. So the sample size is unknown. N is unknown, and that's what we need to solve for. Determine n such that the standard deviation of the distribution of the sample proportions p hat is less than or equal to 1/50th. Okay. So first off, we need to come up with some rule that's going to relate the standard deviation of the distribution of sample proportions. What's that rule going to be? This is your standard deviation of sample proportions. This is the root, square root of, yep, the p, 1 minus p on n. Good. Now, we know what p is in the information. P is a third. Okay? And we're told that this is less than or equal to 1/50th. Okay? So, that's correct. Less than or equal to 1/50th. That's how wide we want our distribution to be. Okay? So we need to select the appropriate sample size to achieve that. So we've got P is, the proportion is a third, times 1 minus a third, divided by the sample size n, and that has to be less than or equal to 1/50th. And there's our little equation we need to solve. Okay? So when you solve an inequation like this, it's good to just treat it as a normal equal to equation, okay, and do the inverse operations to solve for n. So what will be the first operation we've got to carry out? Squaring both sides. We've got to get rid of this square root.
So I don't know, it's gonna more look like this or more look like the previous question.
Both. Yep. Okay, so we've got a third times 1 minus a third, which is 2/3. So a third times 2/3 is 2 on 9. Divide n. Okay. And we're squaring our 50th. Okay? So 2 on 9. Now what's the square of a 50th? Yep. 2,500. 1 on 2,500. And if we multiply by n over to the right hand side to get it out of the denominator, we multiply it on both sides, so it's over here now, and we can then times by 2,500. So 2 times 2,500, 5,000 on 9 is going to equal to n. So that becomes now, when we relate that back to the inequality, less than or equal to, this number becomes the minimum smallest number. So n has to be greater than this amount. Okay? So let's work that out on a calculator. How many times does 9 divide into 5,000? What do we get? 9. Try again. 9 divide 5,000 divide 9. We should say. Sorry. 5. 555. 0.56. Okay, so now this is the number of this is the sample size. So we might be talking about whole number of things or people. So you can't have 0.6 of a person. So the goal here is it says find the smallest integer value of the sample size. So it's whole number, the smallest whole number, where n has to be greater than. Okay, so in this case you have to round up to the next whole person. Okay, so when you go up to the next whole person, if the sample size is greater than this number that you're rounding up to, then that's going to give you, according to your rule, a standard deviation less than 1/50. Okay. So that has to be greater than 556. So if your sample size is equal to or larger than that number of people in your survey perhaps, then you're achieving the smallest or the smaller sample size, your standard deviation of 1/50, or less than that. Okay. Now, why would you might want to do that? Well, the standard deviation, the amount of spread in your distribution, actually becomes a measure of error. From our standard deviation, we can calculate how much error is actually involved in our survey. So when you have a political opinion poll, okay, are you going to vote for Liberal or Labor? And then the newspaper will say, oh yes, there's two-party preferred voting poll of Labor 52 and the Liberals 48. Okay, well there's always a margin of error in those polls, and it might be plus or minus 2 points. Okay, so that margin of error comes from a standard deviation. Okay, a little extended formula which we won't go into, but it draws on the size of the standard deviation, how much potential spread we have in our distribution of values. So you might, to get an accurate opinion poll, okay, then you want that spread or standard deviation to be as small as possible. Okay, so to do that you have to increase your sample size, how many people you're going to survey. So the more people you survey in your sample, the better results you're going to get of the opinion poll. Does that make sense? Josh, you had a question? Okay. Any comments or questions regarding to this type of problem? So the mathematics is just algebraic. It's substitute into a formula and transpose.
So you know when your n is greater than 500?
Yep.
Greater than or equal?
Yep.
Would that change if you ask for the largest integer value of the sample size?
Well, if they want the largest integer value of the sample size, then you're saying you want some maximum number, some maximum sample size. Then that should change the direction of your inequality on your standard deviation. So, what is the maximum sample size you can achieve in order to get a standard deviation greater than a certain amount? Okay, so it's the reciprocal problem. Yeah, it's like thinking about this same problem but with the inequality going the other direction. Okay, but the whole purpose is to minimize the standard deviation, minimize the error in a survey. Okay, so we want to increase our sample size to decrease our potential error in our survey statistics.